Hello. So in this video, we're going to look at the idea of relations. So a relation is a mathematical connection between variables. And usually in this course, we'll limit ourselves to two variables, although relations can involve any number of variables. So when we have two variables, we're going to be talking about the independent variable, which in this case is usually x. If we have multiple variables, we can have multiple independent variables. And we use that to calculate or determine the value of the dependent variable, which again, we're going to usually use y, but we can change out the letters. So relations can take any number of different representations. So here we can see four different representations. We can see one situation in which we have a representation of a relation with an equation. And in this equation, it just straightforward tells us if you have some value of x, here is how you calculate y. You take the value of x times 2, and then you add 7. We will sometimes call x the input because that's what we put into the equation or into the relation. And y would be considered then the output, the result, what comes out when I do that calculation. But I don't necessarily need to have it be an equation that I use to calculate. So we have a second representation right here of a relation that is just simply 4 points. The input being the first variable. You can see here that I accidentally used the French notation for the coordinates of points, or slightly more European maybe, where I've used a semicolon to separate instead of a comma. It means the exact same thing as any old coordinate pair. So this is the point 0, -2. So hopefully that isn't too confusing. But hey, it's good to recognize various international notations as well. So the first variable, the x, is the input, and the second variable, the y, is the output, or again, dependent and independent. Independent comes first. So this, I mean, I might be able to find an equation that relates the x value with the y value. That's not really the point here. The idea here is that I just have these 4 points. So in the case of the equation, I could pick literally any input, pick an x value, and you can calculate a y value. In this case, if I wanted to know what's the output for an input of 4, well, that's actually invalid. None of these points have an input of 4, so that doesn't really work. If I have an input of 0, I get an output of -2. If I have an input of -1, I have an output of 5. If I have an input of 3, I actually have two possibilities. The output could be 5 or -2. So this relation has two possible outputs for a single input. We can also represent relations graphically. So I have a graph over here on the bottom left. This is a collection of points, again, like the set that I just looked at, except for the fact that this is now an infinite collection of points. So I actually could come up with other outputs for other inputs. So for example, if I had an input of 1, x is 1 here, so I could figure out the output by figuring out what is the y value there. So it's approximately -1. I don't think it's exactly -1. With a more precise graph, I could have better ideas, or I could just come up with approximations. I can see, for example, that an input of 0 gives an output of 0. But that graph is just a collection of infinitely many points, as opposed to what I had in the previous case, which was a set of exactly 4 points. And then this last one on the bottom right, this is what's called mapping notation. It's similar to the coordinate pairs. It's a finite number of points. Here it's a little more obvious. What the equation it suggests is that y equals x squared. But we do have to be careful about that, because if I had given you this equation, y equals x squared, that would be any input would be allowed. You could take an input of x equals 2.7 and you could square it and you'd get a y value. But what I have in this mapping notation is more like the set of points, where it is just these 5 values. These 5 inputs are all that we know for sure give us these 5 outputs. So that is a mapping notation. It's a way of really underlining the input-output idea by following the arrows. We can also have situations that are a little more fluid, that don't necessarily have perhaps one specific equation that describes them. So your graph, instead of being sort of generic x and y, could be very specific things. So in this case, the independent variable is time. So independent down here on the horizontal axis. And the dependent variable is temperature. And I haven't given units because I haven't given a scale. Dependent. But we can sort of imagine what's happening here. Temperature of the oven starts out at sort of a room temperature. It's preheating in this B region where it's climbing. It's maintaining its temperature at C. So it kind of oscillates a little. The temperature might drop a bit and then the oven warms it up and so on. D is the cooling phase. And E would be when the oven is off and just sort of holding stable at that room temperature. So we could describe this situation using a relation between time and temperature. And that description could be a graph as I've given here, or it could actually be verbal. Like I could write a paragraph that talks about the fact that at this time, the oven starts at 20 degrees, and then this time we start preheating it, where it gradually raises to this temperature by this time. So we can actually give a narrative description of the relation as well. So we're going to define two sets for relations. The set of all possible values for the independent variable will be called the domain, and the set of all possible values for the dependent variable is the range. So in a lot of cases, these are just going to be all real numbers. So in this first example here, this equation of a line, y equals negative 5x plus 7, my input, or therefore my domain, well, there's absolutely no restrictions on what values of x I can put into this equation. No matter what number you pick, you will always be able to multiply it by negative 5 and then add 7. So the domain is all real numbers. Range can sometimes be a little bit trickier to figure out, but in this case, it's going to be all real numbers again. Y is an element of the real numbers, because it is always possible to get any possible number. So if I think about it this way, if I were to substitute any number in for y, would I be able to figure out a value of x that gave me that y? And yes, I would. I can also imagine the graph of this. So this is a linear function, so hopefully we know those graphs pretty well. Has a y-intercept at 7, a slope of negative 5, so it's going like this. It carries on infinitely, both in a left to right direction, that's the x, all real numbers, doesn't matter how far to the left I go, I will be able to find a point. And it also carries on infinitely up and down. So for y is an element of the reals. For this next equation, y equals 6 divided by x, so my input, if I gave you a number, you would take 6 and divide it by that number. That's the rule for this relation. So the domain has a restriction, because there is a restriction on when we can do division. We are not allowed to divide by 0. So the domain in this case is values of x such that x does not equal 0, but otherwise x is an element of the reals. So this is set notation. We start our set notation by defining our variable. We're using x. This vertical line essentially means such that. It says, here's the variable I'm using, x, and now I'm putting this vertical line because I'm going to give you the rules that apply to x. And then I list the rules that apply to x. The first rule is that x can't be 0. The second rule is that x can be any real number outside of that restriction. So this is the domain of this relation. Again, range can be a little trickier to reason out. I need to think about it. One of the ways that we can find range is by, let's imagine that I wanted to change what was my input and my output. So I'm going to rearrange this equation so that x is isolated in each case. So in the first instance, if I had said, all right, y minus 7 divided by negative 5, that is going to equal x. So then you sort of imagine, if y were the input variable instead, would there be any restrictions on my input? No, there wouldn't be, because I can always subtract 7 from any number I get, and then whatever I have as a result, I can always divide by negative 5. So no restrictions there. So I can do something similar here. Essentially, if I multiply both sides of this by x, I get xy equals 6, which means that x equals 6 over y. So if y were the input, it would be actually the same rule as if x were the input. So because I cannot divide by 0, I have the same restriction on y that I had on x. So for my range, it uses the variable y such that y cannot equal 0, but otherwise y can be any real number. We don't always have to rearrange the equation. You could also reason this out an alternate way, and that would be by saying, if I take 6 and divide it by a number, what sorts of answers can I get? So if I take 6 and I divide it by a negative number, I can get negative answers. If I divide by a positive answer, I can get positive answers. If I divide by really big numbers, I'm going to get really small answers. If I divide by really small numbers, I'm going to get really big answers. But one thing I can never get is 0. The only way to get 0 in a division is if I do 0 divided by something. So 6 divided by something is never going to be 0. And that's why y cannot equal 0. If I have this square root relation down below, so y equals the square root of x plus 4, again, I'm going to have a restriction because there are restrictions for square roots. The square root of something only exists as a real number if the something, the radicand, is greater than or equal to 0. So in other words, x plus 4 has to be greater than or equal to 0 for this square root to give me a real number, which means that x has to be greater than or equal to negative 4. Well, that means that I can write this as set notation. My domain is x such that x is greater than or equal to negative 4, and x is a real number. So any real number greater than or equal to negative 4. The range, I actually cannot figure out the range by isolating x. That wouldn't work, and we'll learn why it doesn't work a little more in future math classes. But I have to reason this range out, and this is actually where I take the fact that this square root doesn't have a plus or minus in front of it, it doesn't have a minus in front of it, so this square root is a positive square root. So in other words, y is the positive square root of x plus 4. That means that y has to always be greater than or equal to 0. Y is greater than or equal to 0, but otherwise y is an element of the reals. If this was y equals negative square root of x plus 4, then y would be less than or equal to 0. There is another way of writing these notations, and this is something called, or these domain and range, this is called interval notation. So I can say x is an element of, so it's greater than or equal to negative 4, so I'm going to write a square bracket, negative 4, comma, infinity, and then a rounded bracket. The square bracket means that the negative 4 is included. The round bracket means that, well, I can never really reach infinity. And for y, then, it would be y is an element of 0 to infinity. When I use this notation, the element of the reals is implied. I don't need to say it. It is already taken for granted with this interval notation. But it tells me that x is found in between negative 4 and infinity, essentially. All right, this next couple, these are graphs. So how can I figure out domain and range from graphs? Well, domain means all the possible x values that exist in this relation. So in this first example, where I have a horizontal line that carries on forever, both to the left and to the right, it exists for every value of x. So if x equals 2, yep, I have a point. If x equals 5, somewhere over here, yes, we have a point. If x equals negative 10, way down there, yes, there will be a point. So x is an element of the reals. No matter what your x value is, there is a value for it. But y actually only ever takes on one value. The points on this graph, well, I've got 2, 2. Or I've got negative 4, 2. Or we've got 0, 2. Or way, way, way off to the right, we've got 1,000,000,000 and 2. The y value is always 2 for these horizontal lines. In fact, we know that the equation of a horizontal line is just y equals some number. So this is the equation, y equals 2. Well, that actually, therefore, is our range, y equals 2. Now, as full set notation, y such that y equals 2, you don't even actually need to put the y is an element of the reals because it can only be 2. 2 is a real number. That's kind of silly. And I actually could do this as interval notation as well. Y is in the interval between 2 and 2, where 2 is included, so square brackets. That interval is basically just a single point, y equals 2. If I wanted to show this x is an element of the reals in interval notation, I would say that it's in the interval from negative infinity to infinity. Round brackets on both sides because infinity is not something we ever reach, and so it's not included. But it's between negative infinity and infinity. This circle, however, is bounded. It does not go off to infinity. For x, it only exists between negative 4 and 2. So in interval notation, I would write this as negative 4 to 2. As set notation, I would write it this way. X is an element of -4, which is less than or equal to X is less than or equal to 2, and otherwise X is an element of the reals. So this is a case where interval notation is actually the better notation. In cases where we just have one excluded value, such as when we did this division, where X cannot equal 0, the set notation is probably better because the way to show this for interval notation is to say X is an element of the interval from -infinity to 0, 0 is not included, so round bracket, or 0 to infinity. I have to break it up into two separate intervals so that I exclude the 0. It's a little bit silly, so the set notation kind of works better. But in a case where X is between some value and another value, the interval notation is a little bit shorter. For my range, the Y values are between -1 and 5. So y is an element of the interval from -1 to 5, because this relation exists between those values, but nowhere outside of them. And again, in set notation, this would look like y such that -1 is less than or equal to y is less than or equal to 5, and y is an element of the real numbers. And in this last example, we just have 4 separate points. It looks like they're in a straight line. I cannot assume it continues forever in this case. It is just these 4 points. So I can't assume that there's an equation that represents them. In this case, the domain is literally just the list of the values of x. So x equals 1, 2, 3, and 4. So I list them, 1, 2, 3, 4. I cannot use interval notation because it doesn't exist everywhere between 1 and 4. 2.7 is not an allowable input. There is no point at 2.7. So I can just list the points. And for y, I list the y values. So I've got -4, -1, 2, and 5. And again, I may think there's a rule here and that I can write an equation, but all I actually have is the 4 points that are shown. So I can't use x as an element of the reals or y as an element of the reals. I can't use interval notation because it is just these 4 points. So I list them.